Welcome to the third video in a series on modular forms, and this video is a bit of digression where we study the modular group SL2Z. Well, SL2Z is the group of all matrices that have integer coefficients and they have determinant equals to 1. So it's actually in GL2Z. And what we'd like to show in this video is that SL2Z is generated by the two elements T, the matrix T and the matrix S. But before that, let us quickly see how does T act on an element of the upper half plane. If you remember, we defined the action of an element of a matrix A, B, C, D. On tau as a tau plus b over c tau plus d. And if we ask how does t act, you will see that t acts on an element tau by translation by 1. And how does s act? S acts as it's just an inversion. It acts as such. So what is this trying to say is that when studying modular forms, remember we define modular forms as these functions that satisfy the a homogeneous equation f of a tau plus b over c tau plus d equals to c tau plus d to the k f of tau. This is a modular form of weight k. It's a holomorphic function with certain properties. And what this theorem is trying to say is that you will know a lot about the function f if you know how f acts on the translation and how f acts on the inversion of an element tau. Okay, so we're gonna prove this theorem, and in the next video we're gonna start by our actual discussion of modular forms. Okay, but first let us see what we mean by T and S are generators. By T and S are generators, I mean, if you take any element in gamma, any element in SL2Z, you can write it as a product of powers of the matrices T and S. Now, if you look at the square of the matrix S, you will see that it is actually the identity. Thus, the highest power of S we want in this expression of A as product is 1, right? And we want to express A as a product. We want to express any generic element of SL2Z as a product of powers of S and T. So let us start by understanding what do T and S do to A when we multiply them by A. So first of all, let me note that it's an easy induction argument to show that t to the power n is just 1 n 0 1. This is easy to prove by induction, right? You just do the matrix multiplication and you observe this by induction. So let us see what happens if we multiply a by t to the minus n, right? If we multiply a by t to the minus n, here's what happens. Let's say A is actually A, B, C, D, and t to the minus n is just 1 minus n 0, 1. When you multiply out this, these two matrices, you get this matrix. You get A and C untouched, and you modify the entries over here as such. So before we discuss further what T is doing to A, let us just understand what S does to A. So if we multiply A by S, right, by the matrix S, what happens is that we switch the two columns of A, we switch these, and we change the sign of the columns that is on the right, of the second column. So why are we doing that? Here's why. So the idea is that we notice that there is a simple case, which is when C is 0. If C is 0, then the matrix should have the form plus or minus 1, B plus or minus 1, 0. And why is that? It's because the determinant of A, which is equal to AD minus B times 0 in this case, is equal to AD, and it's equal to 1 by the definition of SL2Z. So the product of these two entries is 1, but these entries are like they're integers, so they should be both plus 1 or both minus 1. So we can take that sign outside, and depending on this sign, we can say when we take that sign outside, we're gonna have plus or minus next to b. So if you look at this and you remember that t to the n is just 1n 0, 1, you will see that this is just plus or minus t to the power plus or minus b. And we've just written A as a quote-unquote product of matrices T and S, though this is a simple product that has no S's in it. So this serves as a base case if we choose to induct on C. If we choose to induct on the size of C, to perform induction on the size of C, we see that the base case when C is 0 is trivial, and we can actually write A as a product of T's and S. So what happens when C is bigger than 0? What happens when C is either strictly less than 0 or strictly bigger than 0? So here's what we're gonna do. First of all, we may assume that C is positive, because otherwise we can just pull a minus outside, right? We can pull a minus outside this matrix and apply our the argument we're gonna apply right now to the matrix, this one, right? To this matrix. So we may assume that C is positive. And the next thing is that we wanna make an induction hypothesis, which is that assume the statement is true for A equals A, B, C, D with say C less than a certain number R, and then we're gonna prove it for C that is equals to R or has modulus R. So to do that, we will need to notice something about T. So as you see, we have this C now, right? And if we could make this C smaller, right? If we could make this C smaller, we can apply the induction hypothesis, and we get the result that we want. So what we're gonna do is that we're gonna leverage the fact that when we multiply a matrix by S, we switch the columns and we change the sign of the second column. And what we'll try to do is that we'll try to make this D smaller than C, so that when we multiply by S again and switch the columns, we get an element here smaller than C. So to be able to do that, we will need to go back and note something about multiplication by the matrix T. So as you recall, when we multiplied a matrix A by T, this is what we got. Now we ask, there is something interesting here, right? We're fixing these two and we're modifying this. And our hope is to make D smaller, right? So we should choose N smartly, such that when we multiply A by T to the minus N, we get an element here that is strictly less than C. And how can we do that? Well, that is easy, because we can divide D by C. And if we divide D by C, what happens is that you can apply Euclid's division, and you will get D is equal to C times some number Q plus R, where R is strictly less than C, right? So as you see here, R is just D minus CQ, and if we apply to A, if we multiply A by T to the minus Q, we will just get, just as like analogous to what we got here, we will get the same thing as here, except that we replace this N by Q. And if we replace this M by Q, this is D minus NQ is R, and we have R over here. However, there is one thing that we need to notice. The R given by the division algorithm cannot be 0, right? It cannot be the case that we don't have this term, because if we didn't have this term, then C would divide D. But if C divides D, then the GCD of C and D will be equal to C, and it will be strictly bigger than 1. Because if C were 1, we will have also a trivial case, just as the case of C equals 0, right? We will have something like A is equal to 1A, D, and B over here. And since the determinant is 1, this will force that AD minus B is 1. And if we rewrite A, this will be AD minus 1, D and 1. And it's fairly easy to see that if you take the matrix 1A01 and you multiply it by S, right? If you take the matrix 1A01 and multiply it by S, what happens is that you will switch these columns and change the sign of the column that will be placed here, and you'll be getting this column. And if you multiply back by the matrix 1D01, you will be getting exactly this column, and this will be just T to the A, S, and this is D, and this will be T to the D. And you would have written the matrix A as a product of T's and S's as desired. So the case of C equals 1 also goes in the base case, and it is actually trivial to show. So for that reason, we may assume C is strictly bigger than 1. Remember, we entered into this discussion to say that R cannot be 0, because if R were 0, then if we wouldn't have this term, and C would divide D, and in that case we would have a GCD equals to C, which is strictly bigger than 1. But that can't be true, because because in the matrix A we have AD minus BC, which is the determinant, is equal to 1. And it is clear from this identity that the GCD should be 1. So this is all to say that when we multiply a matrix A by T to the minus Q, if Q is chosen by the division algorithm, we get a number here that is as desired. So if we go back to our analysis, right, we're gonna start with an arbitrary matrix now that is of size equal to R, say, and then what we're gonna do is that we're gonna try to make this D smaller than C. Because if we could do that, and we can by the division algorithm that we just explained, we divide D by C and we multiply A by T to the minus Q, and we get that there is an R here that is strictly less than C as desired. And then what we're gonna do is that we're gonna just hit this by S, because if we hit this by S, we're gonna interchange these columns, and we're gonna change the sign of the column in here, and we would have just gotten an element, a new element C prime, that is strictly less than C, right? And we can apply the induction hypothesis to this, and this will be just some product of S, powers of S and powers of T, right? This should complete the proof, because if you bring these invertible matrices to the other side, you would have written A as a product of S's and T's as desired. This completes the proof. So in the next video, we'll be talking more about modular forms and some important constructions.